Good morning and welcome back. So, we're now talking about patterns in the biological setting, and I'm going to have a lot to say about that from a very technical perspective. We're going to talk about reaction diffusion equations and morphogen gradients and the Wolpert notion of positional information. And we're also going to talk about the Turing instability and the work of Alan Turing and how that fed into an alternative picture of patterns and how they form. So before doing that, I want to give a preface, and the preface is really in the form of a very powerful overarching theme, which is that of what I'm going to refer to as the Continuum theory protocol. So the idea here is that we're going to note that there are many, many different ways of viewing the world around us, all of which build upon this notion of the field. And so powerful, so ubiquitous are these ideas that there's an approach that one can take. And what I'm going to do is try to show you the way my book co-authors and I have tried to formalize that. So our starting point is what I'm going to refer to, as I already mentioned, as the Continuum theory protocol, and I want to take an opportunity to introduce this. So we will use that a number of different times, and already in the context of diffusion, you've heard about this, and now I'm just trying to, review the elements of it in sort of general terms. So the first point, so let me just say this analysis or this protocol, as illustrated here, is based on two fundamental examples. The top example, number one, is the example of diffusion, which you've already heard about in this course. The second example is what I will sometimes refer to as hydrodynamics. That word can be generalized in many interesting ways. So in the diffusion context, where we end up, as we've already done, is with the continuum diffusion equation. It's a partial differential equation that describes the space-time evolution of the concentration field. And in the context of fluids, we'll end up with the famed Navier-Stokes equations, which describe the density and velocity profiles in space and time in a moving fluid. And so just to recap what happened already in the context of diffusion, the continuum theory protocol asks us to identify field variables. In the context of diffusion, that was the concentration. You'll recall that at every point in space, we could define a field, which is the concentration. The way that you should think of that is that we visit a particular point, let's call the point R1, and we ask ourselves in a little material volume element, which is represented by this cube, how many molecules are there, and then we divide by the volume of that element. That gives us the concentration. So just to note, C of R and T, where R is a vector, is going to be given by the number in the little box at position R at time T, divided by the volume of that little box, which you can see is delta x, delta y, delta z. So that's the concept. So in this continuum theory protocol, we identify the field variables. In the context of a fluid, what we're going to keep track of is the velocity and also the density. The next idea is that we impose the conservation laws. So, for example, in the context of concentration and diffusion, as you saw already, we impose conservation of mass. When we think later about fluids, we'll impose the conservation of linear momentum. That is to say that we'll examine this little box and we'll make sure that in a time increment delta t, that linear momentum is conserved. Okay, step three, because the conservation law is incomplete in the sense that, for example, it doesn't link flux, which you see on the right-hand side, to concentration, which is the field variable we're trying to determine. So somehow we have to find a relation between flux and concentration, or between linear momentum and velocity, just for example. So this point requires us to do what's called either infer or measure or guess the constitutive law. The constitutive law is this functional relationship between the field variable of interest, which in our case is the concentration, and the flux, which we've used in the context of the conservation laws. The fourth step is to derive the governing field equation, which is usually a partial differential equation, and that is by uniting the conservation law, shown here, and the constitutive law. We do the same thing in Navier-Stokes. We're going to relate F equals ma to the stress, where the stress depends on the gradient of velocity through this quantity d, which we'll talk about later. The details don't matter at the moment. And finally, once we have these continuum theories, we can use them to solve boundary value problems. And that's really, at the end of the day, that's what we want to do with these field theories. We want to use them to reflect on things like the deflection of an airplane wing in turbulence, or a week ago, we had a terrible volcanic eruption in the Pacific leading to a tsunami in Tonga. The way that people would try to build a model of that is by using fluid mechanics equations. Or we might be interested in the Golden Gate Bridge and how it is that in the construction of the steel, the iron is doped with carbon in order to resist material failure over time, which we're used to in the form of rust and such things. So that's kind of the outlook. So we've already said what we're going to do is we're going to kind of step through the various pieces in the puzzle, and I want to start out by just a little bit of a reflection on this idea of identifying field variables. So, the way we identify field variables is through a process of what we're going to refer to as coarse graining. So coarse graining is the idea that we are cognizant that the world is made of atoms or molecules. There's this goes back to Democritus and Lucretius back in the ancient world, and I would say that I don't want to make too strong a pronouncement about whether that was science or philosophy or whatever, but it took a long time, thousands of years, to get to the point where one could take the so-called atomic hypothesis and render it potent in the sense of being able to use it to make predictions about the world and make measurements that validated those predictions. So at any rate, we're going to coarse grain by imagining either the ocean, shown over here, or the atmosphere, shown over here, and we're going to take these little material volume elements that we've already talked about, and we're going to talk about an effective density and an effective velocity associated with those molecules, which have now been replaced by fields. When and how and why is this coarse graining operation legitimate? When is it that we should feel we are licensed to ignore the graininess of matter? It's a super important and interesting question, both scientifically and philosophically. And there's a pat answer to this question. And the reason I say pat answer is because, in fact, it appears that the continuum approach works at smaller scales than one might imagine. So there's two criteria here, and I want to focus on both of them. So two criteria. So criterion number one is that the box should be large relative to molecules. And that's illustrated down here. So here you see molecular dimension D. You see that the material volume element is characterized by a length scale delta x, and hence the criterion that we have in mind is that delta x should be much, much larger than D. So that's criterion number one as to, am I allowed to invoke continuum thinking, this coarse graining operation? Criterion number two is that the spatial variation of the field should take place on length scales much greater than the box size. So what I mean by that is, let's use an example that we're all very familiar with, which is the alteration of the density of the atmosphere as we go upward in the z direction. This is something that a simple hike in the San Gabriel Mountains right behind me will suffice to illustrate. What I mean by that is you can climb a peak like Mount Baden-Powell, but even Strawberry Peak. You can drink your water and close your plastic water bottle at the top of the summit, which in the case of Strawberry Peak is something like 6,000 feet, and which in the case of Baden-Powell is around 10,000 feet or 3,000 meters, and then drive back to the LA basin. And when you get back, you will see that your bottle is crushed. But you won't perceive that change in density, that change in pressure, as you're walking, at the 1 minute time scale. In other words, the spatial variation in pressure, you're probably going to be mounting the mountain at a rate of, like, let's say 5 meters per minute. And so, on the couple minutes time scale, your watch, if it has an altimeter on it, will be sensitive enough to pick up the pressure change. But for you, it'll be more like on the half-hour time scale that you would notice it. Especially if you're descending, you'll notice your bottle starting to crush because the atmosphere is pinching it. So anyway, if my box dimensions are of order a centimeter, that's the scale over which I'm coarse graining the atmosphere. The length scale over which there are variations is 100 meters or something like this. And so the size of the variation, which is 100 meters, is quite large in comparison with the box size. So that's a second criterion. Okay. So the point of this little image is just to note that there's a bunch of different kinds of field variables that we will be interested in. I think I've already mentioned this, but I'm trying to be systematic about this continuum theory protocol and its very broad reach. One of the deep things that physics can bring to biology is this idea of sameness, this idea of things that are ostensibly not the same are in fact the same when viewed through the prism of, for example, field theory. So for example, I mentioned it last time in the previous section in herding, that there's this theory of toner and two that allows us to think about herds and flocks and schools, but it can also be powerful as a tool for investigating the collective motions of actin filaments in a thin layer near the surface of a cell. So ostensibly, who's going to imagine that actin filaments and wildebeest deserve to be in the same conversation? Well, the answer to that is a physicist or somebody that is physics-minded. So here, these field variables, for example, at the top we see scalar fields, and these scalar fields are identified by a single number. I only need one number at position R to tell you about the temperature. I only need one number at a position R to tell you about the pressure, one number to tell you about the concentration. On the other hand, when I think about vector fields, here I need three numbers. I need to tell you Vx, Vy, Vz, or I need to tell you Ux, Uy, Uz in the case of displacement. If I squish a piece of material, if I take this pad of paper and I bend it, I'm bending it in kind of arbitrary shapes, then at each point there's a displacement. If I start with a reference configuration, which I show you here, here's a reference configuration. So I have a position vector at each point in the material, and then I deform it. Now each position is at each part of the material is at a new point, and that new point is given by the old point plus a displacement field, which is a three-dimensional vector. And then, as we've also already mentioned at the bottom, we're going to need to invoke tensor fields, which is, for the moment, if you want to think of it as a 3x3 matrix at each point in the material, that will suffice. It's more rich than that, but that will suffice. Okay, so the next step in the protocol is this idea of imposing the conservation laws, shown here. And I just want to note, again, in the spirit of generality, because that's where we're headed, we're trying to invoke continuum theories. We've already given several examples, but now we're going to invoke them again and again. So we will be interested in the flux out of this central, into and out of this central box. So what we're going to do is we're going to focus on this central box. For the moment, I'm showing you one-dimensional states of variation. And we're going to ask the question, how much stuff enters from the left over here, and how much exits from the right? And conservation of particle number means that the change in the number of particles is equal to the stuff coming in minus the stuff going out. The change in the energy in the middle box is the flux of energy in minus the flux out. Finally, the change in the linear momentum here in the y direction is the flux of momentum in minus the flux of momentum out. So in that sense, what we're going to do is we're going to repeatedly use this idea of flux as a metric for flow into and out, or really a flow across planes, but of different quantities. We can have flow of material in the form of mass. We can have flow of concentration or number of solute molecules. We can have flux of heat across a particular interface or flux of momentum. The next step is this notion of the constitutive law. And I've already alluded to this. We already did it in the case of Fick's law when we talked about diffusion, where we noted that there was a relationship between the flux and the degree of disequilibrium, which we will also refer to as the driving force, which was the gradient in concentration. Note, what this constitutive law does is it links the field variable of interest, which is the concentration, to this quantity of the flux. And we're going to do that again and again. When we talk about heat flow, we measure the gradient in temperature, and that tells us about the flux in thermal energy. Newton's law of viscosity relates the gradient in the velocity to the flux of momentum. So the point is that these constitutive laws tell us how to relate, once again, the flux of some quantity of interest. The flux could be molecules per area per time, energy per area per time, or linear momentum per area per time. All of those are flux quantities. And in each case, they are linearly related to a driving force or a degree of disequilibrium as measured by gradients. So gradients are telling us, they're reporting on, they're a metric of degree of disequilibrium. Note that in each case there's some transport coefficient, which is what mediates this linear relationship between flux and our corresponding degree of disequilibrium. Okay. So the final step in order to obtain our equations is to take these two things, the balance law on the one hand and the constitutive law on the other, and assemble them together, and what emerges is a field equation. So we're now preparing to do that in the context of positional information, the so-called morphogen gradient idea of Lewis-Wolpert and others, and that will lead us to a generalization of the diffusion equation, which we talked about last week, to a reaction diffusion equation, which is a super powerful notion with very broad reach. Okay, I just wanted to say, as I've already advertised, that this notion of the continuum theory protocol is very broad. We can use it in many different contexts. And here I just wanted to note, using kind of a gross example that intrigues me, and I really don't know if it's true, but the claim was made that Native Americans knew or know that a whale will self-cook. Many of us know this from the standpoint of taking a turkey or a chicken out of the oven and letting it stand for a half hour. And the idea is that heat continues to diffuse. So at any rate, the reason I'm showing the whale is because the idea is that once a whale is killed, it will, if left sitting there without cutting it open, it will continue to cook on its interior. And actually, for sure, we can do a calculation showing that the heat does not escape fast enough in order to avoid a large temperature rise. Here I'm just showing you how the continuum theory protocol applies to the temperature field, which culminates in the so-called heat equation, which if you're studious or paying attention a lot, you'll notice that this has the same form as the diffusion equation, which is really cool because what we're noticing is that there's kind of a direct analogy where here, if we replace concentration with temperature and we replace the diffusion coefficient with the ratio of the thermal conductivity to the specific heat times the density, these two equations are the same. And what's wild about that is that it means once you've solved a diffusion problem, you've solved a corresponding heat problem, which I think is very powerful. So, it's just kind of fun. I will just flash this here. I'm not going to spend any time on it, but, this is a really interesting observation about the, knowledge of one problem provides knowledge of another. And we were particularly enamored of, my book co-author Christina and I were particularly enamored of this idea of the correspondence between the heat equation and the diffusion equation, as I already showed you. So with this as my background, what we're going to turn to next is the subject of the reaction diffusion equation, positional information and reaction diffusion equation with special reference to establishing the fly body plane.